So, all right. So in this video, we're going to talk about the method of sections. So for the method of sections, our goal is to be able to determine the force within any member within a truss. So a lot of times this is simpler to apply this method than it might be to apply the method of joints that we covered in the previous section. So what this method assumes, just like the method of joints does, is that the main critical assumption is that since the truss is in equilibrium, we can say that therefore, any section within the truss will also be in equilibrium. So what this is saying, so in order to apply this assumption is that we need to discuss something called an internal force. All right, so internal forces. So if you have a bar, all right, that is in tension, all right, we can do something called a section cut, right, through that bar, all right. So, all right, and what this does is it will reveal an internal surface within the structure or within the member. And you can do that. This is used throughout mechanical engineering, where you can take a section cut through any rigid body to reveal an internal surface. Okay, so what this does is it will give us essentially two rigid bodies now. So we went from one rigid body that had a tensile load at both ends. All right, and after we take the section cut, we now have two rigid bodies, each with an internal force, internal tension force that's equal to the force that's being applied at the ends of the bar. Right? So these are our internal forces. All right. And we could repeat this process for a bar in compression. So we could have a bar in compression, right, compressive force that's acting upon it. We can take a section cut of that bar, and we would end up getting 2 bars. All right, so they still have the the applied loads at the ends. All right, but then we also have our internal force, compressive force as well. All right, so. All right. So we're going to use that to analyze this truss here. All right. So what we're going to do is that we're going to break this truss here in this picture into two sections. We're going to cut the truss into two parts. Right. So we're going to have our first section, which will be the left-hand side of our truss, and then we'll have a second section, which will be our right-hand side of the truss. All right. So the first section, what that will look like is we'll have B section A, B, and C, A, B, and G, A, B, and G. All right, and then we'll have our three members BC, CG, BC, CG, and GF, which we all did our section cut AA through. So our section cut AA that went through these three members. So these will, because we did our section cut through these three members, what we'll say is that we'll have, and the internal forces will now be exposed on these surfaces, right? So we'll have for member BC, we'll have the internal force within that member FBC. For member CG, we'll have the force CG. And then for member FG, we'll have the force FG, right? So because these are internal forces, the right-hand side of the section would also have these same forces. They'd be equal in an opposite direction. So we would have force FFG going in the equal and opposite direction here. We'd have at point, that would be from point E, right? Then at point C, we'd have FCG here going in the opposite direction, and then we'd have FBC going in this direction. Okay, so then the rest of the truss we can draw out just like we had over on the left hand side here. All right, so we still include all of our additional joints here. All right. All right. All right. So then the last thing we need to do in this situation is we need to account for our external forces. So we have 1,000 Newton force that's acting downwards at point A. And then we have a pin joint at point D. So due to the pin joint, we'll have dx and we'll have dy. And then due to the roller joint at pin E, we'll have e of x. All right. So now that we have the left-hand side and our right-hand side of our joint, what we can do now is we can look at which side of this equation would be easier to solve, or which side of the truss would be easier to solve. So the left-hand side of the truss, it has three unknowns. All right, so those three unknowns are FBC, FCG, and FFG. All right, so we can solve those with the equilibrium equation. While if we look at the right-hand side of the truss, we have those same three unknowns, FBC, FCG, and we have FFG. But we also have three additional unknowns. We have d of y, we have d of x, and we have e of x. Okay, so we have 6 unknowns, right? So that's a lot more than 3. So what we would do is after you made your section cut, you would choose the section with the smaller amount of unknown forces, and you would solve for these 3 unknown forces using the equilibrium equation. So to find FCG, you could use the sum of all the forces in the y direction, set them equal to 0, right? You could then take to find FBG, you could take the FBC, I apologize, FBC, you could take the moment about point G, you could sum all the moments about point G, set that equal to 0, and to find the moment about our FG or GF, you could sum the moment about point C and set those equal to 0. So yeah, so once you take the section cut, it just turns into a rigid body equilibrium problem like just in chapter 5. So you just use the 3 equilibrium equations for 2D and solve for the unknowns. So when you're using the method of joints, you are often asked, you'll be asked to determine what is the sense of an unknown member. So what we mean by sense here is we mean, is it intention? Is the member in tension or is it in compression? All right, that's what we're looking for. So you can do this in two ways. This is the same as you did it exactly with the method of joints. All right, so if you have you can use it either by inspection. So what do you mean by inspection is that the equilibrium condition over the entire truss must be true. So oftentimes, if there's only one force that's going in the y direction, you can and it has to oppose a weight like it did in the last example. You know that it has to balance it out. So if you can determine that one of your forces must be acting in a certain direction to ensure equilibrium, so that would be the inspection method. All right, and then the assumption method is if you have is that if you assume that all member forces are tensile and you get a force with a negative magnitude, all right, that member would be in compression. All right. So when you're doing these types of problems, you're you need to you'll do this analysis procedure. So the first step is to draw your free body diagram. So when you draw your free body diagram, the first thing you're going to do is you're going to cut the truss through the truss members that you're interested that you want to solve the internal force in. All right. The second thing that you would do is you would want to determine the reaction at the supports of the truss. So those are typically will be pin or roller joints. All right. And then you will then, after you do that, you can then draw the free body diagram of the section that will have less unknown forces, or less applied forces, I should say. All right, and then the last part is that you would then assume the direction of the unknown forces within the members. So the second thing here is you then apply your equilibrium equations. Typically, you would apply these three, but you could apply multiple moment equations or as well if it makes it if it makes it easier. All right, so when you do this, you should pick the suitable equilibrium equations to help solve for the unknown forces. Pick. All right. So then the first thing that will help you when you do this is that you should first sum the moments about a point where two of the unknown forces intersect. All right, and then the second hint is that if two forces are parallel with one another, sum the forces in the direction that is perpendicular to those parallel forces. All right, so that concludes the method of joints. And we'll do a couple of example problems for you to see, and then you should be able to attempt it during your homework.